The performance of disinfection systems that are used in wastewater treatment, as well as disinfection systems that are used in other applications, is influenced by a combination of factors, including fluid mechanics, principles of chemistry, as well as principles of microbiology. This combination of factors is ideally suited to numerical simulations, and the advances that have been made in recent years in both computer software and hardware are ideally suited to these sorts of simulations. In addition, laboratory and field-based experiments can be used to support and define attributes of these system models. In this lecture, we'll consider numerical modeling approaches that are used to simulate the performance of disinfection systems that are used in wastewater and that should form the basis of design of those systems. Disinfection processes in wastewater treatment have severe constraints relative to most other applications. One way of characterizing the performance of these systems is by conversion, basically the fraction of the influent reactant that remains in the effluent. Disinfection systems have conversion requirements that are typically on the order of 3 to 4 log base 10 units, which again are higher than most other treatment processes. By definition, this requires relatively efficient reactors and provides a great opportunity for optimization of reactor performance. In turn, this also represents a great opportunity for the incorporation of numerical models to simulate the behavior of these systems. These numerical models are fairly complex because they need to account for the relevant physical, chemical, and microbiological phenomena that govern the performance of disinfection systems. That includes specifically fluid mechanics and mixing, the reactions that lead to decay of disinfectants, the reactions that are responsible for disinfection, specifically the kinetics of inactivation, as well as the kinetics of other reactions that may take place in the system, such as formation of disinfection byproducts. In the last decade or two, there have been substantial advancements in software and hardware that have allowed these systems to advance to the point that they can be used now as the foundation for disinfection system design. In fact, they should be used for that basis. Considering first chemical disinfection systems, a fundamental attribute of their behavior is the so-called residence time distribution, or residence time distribution function, oftentimes abbreviated just as RTD. The basic idea here is that fluid elements will go through a reactor system and be characterized by a distribution of residence times. And because chemical disinfection systems have time as their master variable, it's important to understand that residence time distribution in the context of predicting reactor performance. So the residence time distribution function is foundational to chemical disinfection process behavior. In concept, if we know the residence time distribution function and the kinetics, it allows for a description of mixing behavior and ultimately an accurate estimate of reactor performance. In other words, how effectively is this system accomplishing disinfection? Now, oftentimes these numerical simulations are supported by experimental methods such as tracer tests, and I'll mention those again in just a minute. The numerical methods that are used to calculate residence time distribution functions often are based on computational fluid dynamics, or CFD. Generally, when we use these methods, it's possible to develop overall process simulations, and often these simulations are based on the so-called segregated flow model. An important development was made about 10 years ago with the development of the so-called Integrated Disinfection Design Framework, or IDDF. This framework was developed for drinking water chlorination, but the idea is something that can be extended to other disinfectants and other applications. The basic components of the IDDF include a description of fluid mechanics and mixing. Generally, this is done to characterize the residence time distribution function, and this can be quantified using a combination of tracer tests, as illustrated in the image on the right, or computational fluid dynamics, or both. In addition, there needs to be an expression to describe the rate at which the disinfectant itself decays, and an expression to describe the intrinsic kinetics of disinfection and disinfection byproduct formation. Taken together, then, these can be used to simulate process dynamics and optimize performance. Now let's consider this IDDF framework in more detail. First, we need to define the residence time distribution function. Generally, this can be quantified empirically from tracer tests or simulated by computational fluid dynamics. Here's a conceptual illustration of a residence time distribution function. By definition, it is a probability density function. That means several things. First, it means that this product, E of t dt, which is represented schematically by the green stripe in this figure, that represents the fraction of fluid elements that have a residence time between t and t plus dt. In other words, the fraction of the area under the curve that corresponds to that set of residence times. If we integrate that function from 0 to tau, some arbitrary number, that represents the fraction of fluid elements with a residence time less than tau. And if we integrate the entire area under the curve, by definition, that must be 1. So the characteristics of a residence time distribution function are general to all probability density functions and provide critical information about the residence time distribution within a given reactor. Beyond this information about the residence time distribution function, we also need an expression to describe disinfectant decay. Oftentimes this will involve a combination of fast and slow reactions, here illustrated by two reactions that are assumed to operate independently, and therefore their effects are additive. We also need an expression to describe disinfection kinetics. Those kinetic expressions will be specific to the pathogen, disinfectant, and the conditions in the system. In the context of chemical disinfection, let's say with chlorine, that can be influenced by attributes such as temperature or pH. There's a number of models that are available, some of which I've talked about in previous lectures, the simplest of which is the Chick-Watson model, which is illustrated here. We also need then a model to describe disinfection byproduct formation. Now, unfortunately, the mechanisms that are involved in the formation of disinfection byproducts tend to be fairly complex, and they may involve a number of different precursors, some of which are poorly defined. As a result, we often resort to empirical models, such as this one that was developed for total trihalomethanes to predict disinfection byproduct formation as a function of time. All of those pieces of information then are integrated into a numerical simulation to allow us to simulate overall process dynamics and ultimately to optimize the disinfection process. A critical element of those simulations is computational fluid dynamics. CFD simulations are based on the equations of continuity and motion, with the inclusion of a turbulence closure model. The basic approach is that we discretize the system, then define appropriate boundary and initial conditions. From that information, then we can simulate the flow field. Then we link that simulated flow field to scalar quantities of the system, such as the disinfectant reactions and the pathogen reactions. These models have been demonstrated to provide accurate simulations of process behavior, and because of that, they can be used for process optimization. It's much easier to conduct a simulation on a computer than to build a physical prototype. Oftentimes, these optimization strategies involve comparisons of disinfection efficacy, disinfectant consumption, and disinfection byproduct formation. The image on the right illustrates several different aspects of the behavior of different configurations of chlorine contact basins. The various attributes that were included were contact time, disinfectant concentration, total trihalomethane concentration as an indicator of disinfection byproduct formation, and Giardia-Lamlius survival ratio as an indication of disinfection efficacy. If you follow these various reactor configurations, starting from the left with a highly baffled configuration, then fewer baffles moving to the right until we get all the way over to the right in this one, what we observe is that the internal baffles within these systems make a huge difference in terms of disinfection efficacy and overall process performance. And generally, the systems that are more heavily baffled provide conditions that more closely approximate plug flow behavior and that get to a much more efficient reactor design. But the point of this graph really is that we can conduct these simulations on the computer before we go about building a physical prototype or a full-scale system. And those simulations on the computer, because they're accurate, allow us to converge on an efficient reactor design before we actually start pouring concrete. A conceptually similar approach can be applied for UV disinfection. The basic idea here is that we incorporate information related to the intrinsic kinetics of the disinfection reactions that take place within the system. We also need to quantify the influent target concentration. From information based on a simulation of the flow field and the fluence rate field, we can then calculate the UV dose distribution, which governs the performance of the system. The dose distribution is the UV analog of the residence time distribution function I talked about previously related to a chemical disinfection system. If we can quantify the dose distribution, oftentimes using these numerical simulations, then we're in a position to accurately simulate the performance of this reactor relative to any disinfection endpoint. Fluid mechanics and the fluence rate field will be governed by reactor geometry and configuration, the flow rate through the system, lamp type and lamp power, as well as the optical characteristics of the fluid being treated. Again, this approach is analogous to the numerical simulations that I described previously under the IDDF that have been developed for chemical disinfection systems. But in these systems, because of the nature of photochemical reactors, where we see these strong gradients in local reaction rate, accurate simulations of fluid mechanics turn out to be vital to accurate simulations of photochemical reactor performance, such as UV disinfection systems. Accurate simulations of the fluence rate field are a unique requirement of UV disinfection systems. There are a number of tools that are available to conduct these simulations, but the best of these is based on a method known as ray tracing, which is illustrated in this image for a low-pressure mercury lamp. The basic idea in a ray tracing simulation is that we'll draw a numerical representation of the lamp or lamps within the system, and then we'll simulate the output by accounting for the relevant optical behavior of the system. So the components of those simulations include the arc itself, where the radiation is being generated, as well as reactions that take place at surfaces that include reflection and refraction, and those reactions will take place at every interface where there's a change in refractive index across the interface. Ray tracing simulations have been demonstrated to provide accurate, detailed numerical representations of the fluence rate field within systems. Moreover, these ray tracing simulations compare favorably with both measurements and numerical simulations using other methods. Ray tracing can also be incorporated into an overall simulation of disinfection efficacy. In general, this is going to involve a flow field simulation by computational fluid dynamics, a ray tracing simulation of the fluence rate field, a model to describe the intrinsic kinetics of microbial inactivation, for example, the first order model or single event model. And then what we'll do is simulate disinfection efficacy by first calculating the dose distribution and then integrating that dose distribution using the segregated flow model. In this segregated flow model, which is illustrated here, the function over on the right, E of d dd, represents the dose distribution function. And the function indicated in the parenthetical entry of the integrand n over n0 batch, that describes the intrinsic kinetics of disinfection. If we have those two pieces of information, the intrinsic kinetics and the dose distribution, again, we can integrate them using this model to provide an accurate prediction of the fraction of microorganisms that are going to be inactivated by the reactor. And that's the ultimate goal of these simulations. Those simulations have been demonstrated to provide accurate representations of the performance of these systems and the effects of photochemical reactions more broadly. Because those simulations are so detailed and provide so much information, and because they're accurate, it's also possible to incorporate them into a stochastic approach. For a given set of input or operating conditions, the model predictions are going to be deterministic. So if we want to follow a stochastic approach, what we need to do is to allow those input parameters to vary. And in fact, observations, measurements from the real world demonstrate that many of those input parameters do vary. So in this stochastic approach, what we do is allow for variation in things like flow rate, lamp power, and the optical characteristics of the system, such as transmittance at a characteristic wavelength like 254 nanometers. We conduct those simulations over the range of those input process variables, and then that allows for a process evaluation that includes the effects of variability. This approach allows for improvements in process reliability and at the same time allows for optimization, reducing the overall cost and operating costs of these systems. Summarizing then, disinfection process design is based on decomposition of process behavior. Basically, we're following a traditional chemical engineering process engineering approach. What we've done is decompose the process to evaluate the attributes of the system that influence its performance. Those include fluid mechanics, disinfection kinetics, the kinetics of other reactions such as disinfection byproduct formation, and other relevant phenomena, for example, in the case of UV systems, the fluence rate field. The experimental and computational tools that are available now allow for accurate quantification of process behavior. And in fact, stochastic approaches have emerged over the last few years to facilitate optimization of disinfection system design and to incorporate variability.